In this lecture, I am going to introduce you to the notion of equivalence of matrices. And also tell you what it has to do with isomorphism of modules. To start with, let's look at the definition of equivalence of matrices. This is an equivalence relation on rectangular matrices over a commutative ring R. So let R be a commutative ring, and let's say M by N R denotes the space of all M by N matrices with entries in R. This is not a ring, it's just a set. Definition: we'll say that X, Y in M and R, we say that X is equivalent to Y if there exist two matrices A in GLM R and B in GLN R such that Y is equal to AXB. So it's not difficult to see that this is an equivalence relation. It follows from the fact that this is basically an action of the group GLMR cross GLNR on M by N. This will be M by N here. And these equivalence classes are called equivalent matrices. So the relevance of equivalence of matrices to the study of modules comes from the following theorem. If X is equivalent to Y, then you can look at the module Rm mod the column space of X. This is going to be isomorphic to Rn column space of Y. Isomorphism of R modules. We've already seen that every finitely generated module over a Noetherian ring is going to be of this form. And so now once we have the matrices, we can also use this equivalence notion to try to understand when two modules given in this form are actually isomorphic. So how do you prove this? So recall, what is the column space of the matrix X? The column space of the matrix X is nothing but all vectors of the form X times V, where V is a column vector in Rn. So if X is an M by N matrix. And now suppose B belongs to GLN R and Y is equal to XB. Then column space of Y, well, that's YV, V belongs to Rn, but that is XBV, where V belongs to Rn. But I can think of this BV itself as a vector in Rn, so this thing is contained in the column space of X. Okay, and since B belongs to GLN R, B has an inverse. And I can write X equals Y B inverse. So then I can apply the same argument by replacing the role of X with Y and B with B inverse, and I get that column space of X is equal to column space of YB inverse, which we'll see is contained in column space of Y. So then together this means that column space of X is equal to column space of Y. So firstly what we see is that Rn mod column space of x is equal to Rn mod column space of y if y is equal to x times b, where b is in GLNR. So this is one side of the notion of equivalence, that y is x times b. What about the other side? So let's now look at the case that y is a times x. A belongs to GLMR, and so this A defines an R module homomorphism Rm to Rm. Let's call it T subscript A. What does this do? T subscript A of a vector v in Rm is just A times v. Now what does T subscript A do to the column space of A? X. So if I take T subscript A and apply it to the column space of X, then that means I'm applying T subscript A to vectors in the column space of X. What are vectors in the column space of X? Well, they're vectors of the form xv, where v belongs to Rn. But what is TA of xv? Well, TA of xv is AXV, where v belongs to Rn. But AX is y. And so this is the column space of y. So what we see is that TA maps the column space of X exactly onto the column space of Y. And because A is in GLMR, this TA is actually an invertible R module homomorphism, and therefore it's a bijection. So T subscript A maps the column space of X bijectively onto the column space of Y. It's an isomorphism of the column space of X onto the column space of Y. So T subscript A is from Rn to Rn, and you have this quotient map from Rn to Rn mod column space of X, and you have the quotient map from Rn to Rn mod column space of Y. But this map T subscript A takes the column space of X onto the column space of Y. So it gives rise to an isomorphism T subscript A bar, defined by T subscript A bar of V plus column space of X is equal to TAV plus column space of Y. And this fact that T subscript A maps the column space of X isomorphically onto the column space of Y says that T bar A is a well-defined isomorphism from Rn mod column space of X to Rn mod column space of Y. I'll let you check that yourself. Now we are ready to the general thing. Suppose that y is AXB, where A is in GLMR and B is in GLNR. Then Rn mod column space of X is the same as Rn mod the column space of X times B, but that's isomorphic. Sorry, this should be Rm mod the column space of AXB, which is Rm mod the column space of Y. I guess all these n's need to be m. That's it, that's done. So what we get is that if two matrices X and Y are equivalent, then when you think of them as matrices of relations, they define isomorphic R modules. So if I give you two matrices, M by N matrices with entries in a ring R, how will you decide if they are equivalent or not? So this is a decision problem. Determine if X is equivalent to Y. These kind of decision problems usually are dealt with in two different ways. One is the method of finding canonical forms. So the idea is that for each equivalence class, you find a specific representative which has a very nice form. And you can take each element in that class and you perform a certain algorithm, you would reduce it to an element in the canonical form. And the other is that given an element of your set, you just try to compute certain invariants. So you just take the matrix X and compute some numbers with it. And if you have another matrix Y and you compute those numbers and they turn out to be the same, then X is equivalent to Y. So we have these two approaches, canonical forms and invariants. We'll see that actually the canonical forms approach actually leads us to the discovery of the invariants. Let's begin with a very simple example. Let's just take the case where R is equal to F, a field. Okay, so the theorem is every matrix X in M by N F is equivalent to a unique matrix of the form. So the form is very simple. You have 1, 1, 1 up to some time, and then you have 0, 0, 0 after that, and everything else is 0. So you just have a principal diagonal worth of 1. This is a rectangular matrix, and then you have zeros. And the proof is not very difficult. Let me first illustrate it with an example. So remember the description of GLMR and GLNR. Well, that works also for a field. So let's start with a matrix like this: 1, minus 1, 0, 0, 1, minus 1, 1, minus 2, 1. And let's try to figure out what its canonical form is. So we'll try to reduce it. This thing is called a canonical form. There's a unique matrix of this kind in each equivalence class. So let's try to reduce this to a canonical form. So what we want to do is we want to get zeros here and here. So what I'll do is I'll try to take this this 1 here and try to make it 0. Okay, so what I'll do is I will take the third column and subtract from it the first column, and what I get is right multiplication by one of the shear matrices. So it's still in the same equivalence class, and this only changes the third column, and what I get is 0, minus 1, 1. And now I'll try to make this entry here 0. And so now I'll do a row operation. I'll take the second row and add it to the third row. R2 goes to R2 plus R1. And now what you'll get is 1, 0, 0. Add the first row to the second row. I'll get 0, 1, minus 1, 0, minus 1, 1. And now what should I do? I want to make this entry in the second row and third column 0. So I'll take the third column and add to it the second column. So let's do it like this. Take this third column and add to it the second column. And so what I get is the matrix 1 0 0 0 1 0 0 minus 1, and here I will get also 0. And now I can take the third row and add to it the second row. So what should I do? I'll take R3 and take it to R3 plus R2. And what do you get? You get the matrix 1 0 0 0 1 0 0 0 0. And this is indeed a matrix of this canonical form. So what we've done is we've started with a more general matrix, and by a series of row and column operations we have reduced it to the canonical form that we desire. And you can take this process that I've used. I've actually been following an algorithm. So let me enunciate for you this algorithm. So if A is 0, there's nothing to do. It's already in a canonical form. This row, there are no ones, so it's just 0 everywhere. And otherwise, what you do is, by interchanging rows and columns, make sure that A11 is not equal to 0. I mean, you have a non-zero element somewhere in your matrix, say in the ith row and jth column. So first you interchange the ith row with the first row, and then the jth column with the first column, and then you would have moved that element from the ith row and jth column to the first row and first column. Okay, and now what we'll do is we will kill all the elements of the first row and the first column except for the element in the first row first column, the corner top left element. So what we have is this situation. We have A11, A12, A1n, A21, AM1, and we have whatever here. I'm not particularly interested in what's over here at this moment. I'll just put a star here. And what I want to do is I want to kill all these things. So what you do now is you take Ri and replace it by Ri minus AI1 by A11 Ri. So this A11 is non-zero, so and we are working over a field, so we can definitely divide by A11, and this will have the effect of killing off the element AI1. And so you do this for I equals 2 to m, and then what you also do is Cj goes to Cj minus A1j by A11. Sorry, this should be R1 and this should be C1 for j goes from 2 to n. And so now what you got is you've taken this matrix and you've made all these entries 0. Right, let's use. And you've got some matrix here, A prime, let's call it. And now what you can do is you can repeat similarly with A prime. So what you can do is you can interchange rows and columns of A prime and make sure that out here you have a non-zero element, and then use that to clear out one more row and one more column except for the diagonal entry. And when you do these operations on A prime, because the corresponding elements in those rows and those columns in the first column and first row of A are 0, they will not really disturb the first row and first column of the bigger matrix A. And so any row or column operation involving rows 2 to m or columns 2 to n will not affect the first row or the first column. And eventually you'll be able to reduce your matrix to reduced this canonical form. So what is the meaning of all this? So firstly, what we note is that there are minimum mn plus 1 possible canonical forms, right? Equivalence classes. Namely with 0 ones, 1 1, so on up to minimum mn ones. And the class of the matrix 1 1 1, where you have r ones and then 0, consists of all rank R matrices. Because if you left multiply or right multiply a matrix by a non-singular matrix, then you will not be changing the dimension of its column space, and so you will get a matrix of the same rank. So if your original matrix had some rank, but then you reduce it to this canonical form with rank R, then the original matrix must have had the same rank R. So now we have found the invariant that we wanted. So we have the canonical form, and the invariant is x is equivalent to y if and only if rank of x is equal to rank of y. And there's even an algorithm for computing rank. What is rank of x? It's the smallest integer r such that all smallest non-negative integer r such that all r by r minors of x are 0. You may have seen this in your linear algebra class. So this rank has a very nice interpretation in terms of the matrix and is therefore easy to compute quite directly.